So for our limiting reactants, okay, let's just jot down just a couple things, and then you will have the work time, okay? So limiting reactants. This is just a reactant that is going to limit the amount of product that can be made. Okay? It limits the amount of product that can form in a chemical reaction. The reactant that gets used up first. So reactant that gets used up first, that's another way to define it. And once it's used up, the reaction is going to stop. So ultimately, your limiting reactant stops the reaction. Okay? By the way, RXN is shorthand for reaction. All right. So our limiting reactant is ultimately the thing that decides that something's going to stop. So in our lab on Monday, okay, we had baking soda in our beaker. We had hydrochloric acid. So when we put the hydrochloric acid in with it and it reacted, it kind of fizzled and stuff like that. And we let it fizzle, and then we kind of did a little stirring motion just to make sure, and it was fizzling some more, and you did it again. And you kind of kept doing that until it stopped fizzling, because what that meant was it stopped making carbon dioxide, right? Who was your limiting reactant? Was it the hydrochloric acid or the baking soda? It was baking soda, yeah. And if you didn't know that, that's okay. But ultimately, if I would have had you calculate stoichiometrically the two amounts that could have possibly been made, you would have seen that it produced the least amount, all right? But just from looking at it and not really being familiar with how to find a limiting reactant, you could have looked at it and seen that, well, the hydrochloric acid, you saw a clear liquid left over, right? It wasn't really a white powder anymore. So you could kind of say, well, it looks like it got used up, or it all got dissolved, or something like that. And that's pretty fair as well, all right? So when I go to dispose of your guys' waste beaker, I'm going to have to neutralize it some more, because there was a ton of acid still in it, right? And I know that. So it definitely wasn't completely neutralized. All right, so our excess reactant is the opposite, right? So this is the one that is not used up completely in a reaction, which means that once the reaction stops, there will be some of this reactant left over. So once the reaction was stopped, that one is left over, and we like to ask you guys how much is left over, okay? So the steps that are described right here are great, and I actually finally used them today. I've been doing this for a while, but I've never taught it that way, and I was like, oh, that's cool. However, I don't want you guys to run into a little hiccup of thinking that you have to memorize something else. So I'm going to go ahead and teach it the way that I used to, which is that you are going to run two small stoichiometry equations. You find the smallest, that's your answer, all right? This one you got to kind of think about, and some of you guys will be able to read that and be like, oh, yeah, I get it. So cool on you, but for the most part, let's all just learn it the other way. So this is my method, okay? You're going to pick one of your reactants. Pick one product. So looking at your balanced equation, you're going to pick one product and use stoichiometry from each reactant. Okay, so you're going to pick one product and use stoich from each reactant. Okay, meaning you're going to run two stoichiometry problems. Okay, if you technically have 3 reactants, you should be running 3, but hopefully that doesn't happen. All right, so that's your first step. Second step is the smallest answer reveals the limiting reactant and the amount produced, right? So that last part, the amount produced, that makes sense, because that kind of goes hand in hand with what we saw with our recipes, right? We can only make as much as the one that we're going to run out of first, right? So you're always going to be picking that smallest answer for that, Okay, so we'll come back up to see the example that they put right here, but we're going to base it off of this problem still, all right? So I'm going to kind of write our work right here because it won't take up much room, I promise. So looking here, it says if 2 moles of HF is exposed to 4.5 moles of silicon dioxide. Notice I had to underline 2 things. And then it's asking what is the limiting reactant? And you're like, oh man, so much for the circles and the underlines. So when you see that and you know that it has to do with limiting reactants, or if it says how much product is created, that's a limiting reactant because you have 2 things that you had to underline. So what this is going to look like, we're going to pick one product. So do you guys want to do silicon tetrafluoride or dihydrogen monoxide? Silicon tetrafluoride? Okay. All right, sounds good. So we're going to go ahead and pick that one. Okay? All right, so I'm going to base both of my stoichiometry calculations from our reactant to that, okay? So I'm going to go ahead and start with 2 moles. I'm going to write it right here. 2.0 mole of HF, okay? I'm going to bring words down to the right. I was in mole town, so what does that mean my first step always is? Cross the bridge because it's a mole ratio. Good. Okay, so mole HF, we're going to cross the bridge to SiF4. Okay, so looking up at the balanced equation, HF has a 4, SiF4, has a 1. Okay, so I have 2 times 1, which is 2, divided by 4. What is that answer? 1/2, 0.5. Okay, so 0.5 SiF4. All right, so that's our first answer. So we tried it out. Now we're going to look at the other guy. We have 4.5. I'm trying to think where I can squeeze this. I'll put it right here. 4.5 moles of SiO2. And I'm going to, I don't think I can write and talk at the same time, sorry. We're going to be crossing our bridge again from SiO2. So up in the balance equation, that's a 1. And we are solving for SiF4, right? Which is a 1. So what does that answer come out to be? 4.5. All right, so which one is my answer? Is it the 0.5 or is it the 4.5? It is the 0.5. This is the only one possible. This is not, which means that my SiO2 is my excess reactant. My HF was my limiting reactant, which ultimately was the question they were asking. Okay, so that's what you're looking at. Okay, you're doing 2 stoichiometry calculations. You're picking the smaller answer. Whoever it came from, that's your limiting reactant. Okay? Okay. So let's look at the first practice problem, and then I can go back and show you what the other method looked like. Okay? So it says 0.75 moles of N2H4 is mixed with 0.5 moles of H2O2. So once again, 2 underlines meaning limiting reactant. So it says, what is the limiting reactant or how much do we make, right? So we're going to go ahead and run 2 stoichiometry rounds. Okay. Oh, silly me. What should I solve for? What do you guys want to pick? We have N2 or we have H2O? Do the N2? All right. Sounds good. So we're going to go to N2. So we'll go moles N2H4, moles N2. All right. So now looking at the balance equation, I have a 1 down here and a 1 up there. So what is the answer? Yep. 0.75 moles of N2. Okay. All right. The next one, we have 0.5 moles of H2O2. Does anybody know what H2O2 is? That is hydrogen peroxide. Yep. Oh, were you about to say? Sorry. Good job. All right, hydrogen peroxide. So, okay, so bring words onto the right. We got that, hydrogen peroxide. And we are going to, so big thing to remember, you have to compare it to the same product, right? So we have to leave it N2 on top. So that tells me a 1 on top. H2O2 has a 2 on the bottom. So 0.5 times 1 is 0.5 divided by 2, 0.25. Okay, so who is my limiting reactant? Good, there we go. Okay, so this is the only one that's possible. So it means that if I were asking, okay, what's my theoretical yield of nitrogen? That's the answer. This one can't happen. Okay, so to answer the question, they said limiting reactant is hydrogen peroxide. Okay. Part B is saying how much of the excess reactant is left over. So my excess reactant was the other one. So N2H4. So we have to figure out how much of that was actually used up, right? So you have two options. You can either go to what your answer was and go backwards to N2H4, or take what we do know, which was that it was based off of this H2O2. So 0.5 moles of H2O2. And we're going to relate it to N2H4 to figure out how much was used. So H2O2 has a 2 in front of it. Okay, again, we're pulling from our balanced equation right here. So a 2. So we have that, and then our N2H4 still has a 1. So 0.5 times 1, 0.5 divided by 2, 0.25. So 0.25 moles of N2H4 were used up. So how much remains? What are we going to do? Subtract what? Good, good. So we're going to go back to what the question actually started with. It said 0.75 moles of N2H4. We're going to subtract what was used up. Okay? And from there, we get how much is left over. Good. Okay. So I'm going to continue this page probably more tomorrow. Hold on. Oh. So just so you know, so some of you guys, like I said, will be able to read that and you understand it, and that's cool. Basically, what this was asking you to do is what you saw that we kind of did right here, where we set it equal to the other reactant, okay? Or not equal to, but we based it off of both of the reactants and how they compared, so you could figure out how much got used up. Once we knew 0.25, we would have checked what the original value was to make sure we had enough. If we only needed 0.25, but we had 0.75 available, then that told us that the limiting reactant was H2O2. But do you see how you could get confused if you don't slow down enough to actually grasp that concept, all right? But if you can, then cool, because you'd only have to calculate one thing, right? But so I will be more than happy to help anybody out who is hoping to do it that way. All right. But I'm going to go ahead and stop this recording thing.